In this section of chapter 4, we discuss how to calculate the area between two curves. So the setup goes a little something like this. Let's say we have a region bound between two curves, say y equals 3x to the 1/3 and y equals x minus 2. Now, if you'll notice, part of the graph, right, is below the x-axis, right? We've got this portion here. Here's the x-axis. And we've got this portion that's below and this portion that is above. And it may at first blush think, well, if we were to integrate this area, we'd get a negative area. And if we integrated that area, we get a positive area. So how could we use the definite integral to compute area? But it turns out that the signs will work themselves out. So let's review this problem. Let's take both curves. Let's take the top bound here and the bottom bound here and add 2 to it, right? So we're going to just lift the whole graph up by 2, which will bring everything above the x-axis. So we add 2 and our graph will look something like this, right? So we've added 2 to the function x minus 2, which just gives us y equals x. And then we added 2 to this, so that everything just got shifted up 2. And now the whole area is positive. It's definitely above the x-axis. And what we can do here then is we could integrate up to this curve, right? We could integrate that curve and get the area under that curve. But then we'll have too much, and so then we could subtract the area below this curve. Well, this whole integral would be the integral from 0 to 1 of 3x to the 1/3 plus 2 dx, right? That would be that area. And this area here would be the integral from 0 to 1 of x dx. So if we were to subtract the 2, we should get this red region, the region that we're after. What is that area? So let's call these two things. Let's say the entire area is, I don't know, we'll call it the whole area being C. That's what this integral is, right? This gives us C. We'll call the area we're after, we'll call this A. That's the area we want, and we'll call this area B. And so we get that A, the area we're after, is equal to C minus B, right? And C, the area we're after, or sorry, C is the integral from 0 to 1, 3x to the 1/3 plus 2. That's C. And then B is this integral, 0 to 1, x dx, right? Okay, so let's kind of work this out. So what do we end up getting? So first off, I've got the same bounds of integration, 0 to 1, 0 to 1. So I can combine these two integrals, right? So A is equal to the integral 0 to 1, 3x to the 1/3 plus 2 minus x dx. Or I'm going to write it another way so that we could see what actually happened here. This is 0 to 1, 3x to the 1/3 minus x minus 2 dx. And notice how this relates to the original problem. X minus 2 was our lower bound, whereas 3x to 1/3 was our upper bound. And so what we're really looking at here is the difference of the, this is our, in the original problem, this was our upper bound. And this is our lower bound. So we'll be able to generalize this and say, okay, if I've got a region that is bound above by some function and bound below by a function, if I take their difference and integrate, I'll find the area between them. And this is by no means a proof, but it is suggestive that what did we do? We said, okay, well, I don't like the fact that this is below, so I can shift everything up. But the shifting and subtracting really didn't change a thing. Alternatively, we could have broken this into two parts and just said, here's this part above the x-axis, here's the part below the x-axis, and the area that we're interested in would be the whole thing. So it'd be C is equal to A plus minus B, because this part would be negative. And it still turns into the same thing. So let's calculate this integral. What is the area of the bounded region? Well, we know how to do antiderivatives, and the fundamental theorem of calculus says, okay, let's just go ahead and antidifferentiate. So I'm going to say this is 3 times, so I add 1 to the exponent, so that becomes 4/3. And then I multiply by its reciprocal, so 3/4. That deals with that. I've got a minus 1/2 x squared, and then I have a plus 2x, and that's all between 0 and 1. So that's the antiderivative of this expression here. And so evaluating, I could put a 1 into everything, so this is equal to 9/4. Since the cube root of 1 is 1, 1/4 is 1, and this is 9/4, minus 1/2 plus 2. And then when I put 0 in, everything cancels out. So there's nothing to subtract there. And this is equal to 11/4. So regardless of how we approach this problem, leaving it alone, the area would be 11/4. Or doing this shifting business, the area would be 11/4. So in general, what we can say is if say f of x is bigger than or equal to g of x on the interval AB, right? So on the interval AB, then the area between them is given by the integral of f of x minus g of x with respect to x. And our bounds will be from A to B, right? This is the area between two curves. So let's find the area between, say, the curves y is equal to sine of x times cosine of x, and the line y equals 1 for x between 0 and pi over 2. So we've got to figure out, before we integrate, before we compute integrals, we have to figure out which one's bigger, right? So by definition, if f of x is bigger than g of x, then we just subtract and integrate between across the domain. But we got to know which one is bigger. So a little bit of algebra here. We do know that between 0 and pi over 2, both sine and cosine are positive. And we know that sine and cosine can't get any bigger than 1, right? That's just a fact. Between 0 and pi 2, this is always going to be true. And if that's true, then their product, putting this together, since they're both positive and they're both less than 1, then sine of x times cosine of x is less than or equal to 1. It's also positive, but really the key fact that we want to know here is that this product is less than or equal to 1. So 1, y equals 1, is the larger function, and so the area will be given, the area between the two curves will be given by the integral between 0 and pi over 2, 1 minus sine of x cosine of x dx. So I'm going to break, unlike the other one where I put them together, I'm going to break these two apart. And the reason why I'm going to do that is because I'm going to have to do u substitution to deal with this product here. Whereas I can take the antiderivative of 1 all day long. It's going to be x. But to do the integral of sine of x cosine of x, I'm going to have to do some kind of u substitution. So I'll break it up. And so this is equal to the integral between 0 and pi over 2, 1 dx minus the integral 0 to pi over 2 sine of x minus cosine, or times cosine of x dx. And so what's my u sub going to be? Well, I can either be sine or cosine. Doesn't matter. I'll just go ahead and say u is equal to sine of x. Then du is equal to cosine of x dx, which is right here. So this is my du, this is my u, and I need to change my bounds of integration still. So u of 0 is sine of 0, which is 0, and u of pi over 2 is sine of pi over 2, which is 1. So putting that together, I can go ahead and anti-differentiate this. So this is equal to x in between 0 and pi over 2 minus the integral. Now the lower bound is now 0, so it's still 0, but the upper bound is now 1, and it's u du. And x between pi over 2 is just equal to pi over 2 minus 0 minus, and then this is going to be 1/2 u squared in between 0 and 1. And that's going to be a 1/2 minus 0. So this just ends up being pi over 2 minus 1/2, or more simply, pi minus 1 over 2. So that's the area between these two curves, the area between sine of x times cosine of x and y equals 1. That's what the area looks like. Or that's not what the area looks like, but that's the value, the quantity of the area, pi minus 1 over 2.